I want two of you. I want you to come and help me build a molecule. Would you like to come?
Yeah.
Would you like to come? What we've got here is two chemicals from oil. Come round here, and you come round here. All right? Okay? Now, I'm going to mix the two chemicals, and if you look, you'll see that we've got two layers. One chemical from the oil sits on top of the other. One is an amine, and one is an acid. And you do it fairly gently, we'll get two layers. Can you see the two layers? Right. Now, where the two layers have touched, the molecules have joined together. All right? And I'm going to lift out the joined together molecules. It's all wet and gooey at the moment, but as I pull it out, one molecule from one layer joins on with one from the bottom, which then has one from the top and one from the bottom. They keep joining together. Now, got a nice firm grip? Would you like to hold this? Hold it tightly, right, so you don't drop it. Now, very gently walk away that way. Gently, slowly, 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 keep going. And as he keeps pulling, the molecules keep joining together, and you're making a longer and longer chain of lots and lots of molecules. Right, stop. Now it's going to get a bit droopy in the middle, so I want you to help by picking it up here. Try not to break it. Keep pulling gently, both of you together. Take it with you. That's right. Keep going. And what we're doing is shown by the model coming out of the bucket there, where we're joining the molecules together, one onto the other. Whoa! And we have got this long chain of molecules, millions and millions of them, joined one to the other to give us this, which is nylon. Okay, thank you very much. Would you like to go back? Mind the model as you go. You have to step over it. Just think for a minute what this means. From the oil, we've got something like the nylon. We could join molecules together in all sorts of ways to give threads, and I want you to do something with you when you go home tonight. When you get changed, I want you to look in the labels of all the clothes you're wearing, everything you're wearing, and see if it says nylon or polyester or acrylic or terylene. Because if it does, then it was made in a reaction just like you have just done now in a factory. And there's the thread of nylon being pulled out and spun in a factory to make all these synthetic fabrics that you wear every day, probably even without thinking about it. We don't necessarily just have to make threads. We can turn our molecules from the oil into nice clear plastic sheets for cling film and polythene. Or we can turn them into nice waterproof materials to make, like PVC, to make mats and anoraks and things like that. And we don't necessarily have to join the molecules together to make threads. We can join them together to make something else, as Mike is going to show you.
Right, we can turn the molecules that we get from oil not into molecules that give us materials and substance, but into molecules that give us colour. And Anne's going to demonstrate one reaction here that produces a new chemical with a bright colour. Now, up until about 100 years ago, most of the dyes that we used, in fact all of the dyes that we used, were available purely from plant sources. They weren't synthetic, they weren't man-made, they were extracted from plants. But around about the turn of the century, a reaction was developed that produced a new chemical with a bright colour. Now this reaction comes in two parts. The first mixture produces one of the chemicals, and with the white cloth soaked in that chemical is then lowered into the second chemical, and as you can see, the first two chemicals combine to give a bright orange colour which dyes the fabric. Now we can be quite fussy about these dyes that we make. Together with the synthetic fibres and the fabrics that we've got, we can make synthetic dyes and control the shape and structure that their molecules have so that particular coloured dyes are absorbed onto particular types of fabric. And what we have here is a mixture of 3 different coloured dyes in a dye bath, yellow, green and red, and 3 different fabrics. The dye molecules are designed in such a way that one dye sticks onto one particular type of fabric, so that you can pull out 3 quite different colours. You can see from the tails here that each cloth would have started off white. So you can design molecules to produce particular colours which are then absorbed onto particular fabrics and no others. Now this can be used as an illustration, if you like, of the difference between the way things are now and the way things used to be in Victorian times. We have here some clothes that have the same sort of colour that you might have expected to see about 100 years ago. Very, very dull, very, very ordinary. And to contrast with that, we've got some fabrics here that have been dyed with synthetic dyes, and you can see the entire range and variety of different colours that we can produce synthetically. Okay.
The molecules can do amazing things. Just think for a minute of the colours that you get in a flower or on a butterfly's wing. And just think also, if you were lucky enough to see a glowworm or a firefly in the dark, then these little beetles and insects have a very special chemical reaction that goes on in their bodies. It allows them to flash coloured lights to attract their mates. And this special light flashing is produced by a reaction, and it's called a chemiluminescent reaction. And when scientists discover things that are as fascinating as that, they want to understand them and they want to try and mimic nature and do similar sorts of things. Well, we've known that there are special effects of light, that if you take UV light, which your eyes can't see, there are some chemicals that can absorb it and give it back to you as visible light. So if we can have the lights down, please. This rock is called fluorspar because it gives back the UV light as visible light, and this is called fluorescence. And this is a chemical called fluorescein that is giving us back the visible light. And in here we've just got some ordinary washing powder, because it's this property of the molecules in the washing powder that they add to the mixture that makes the washing look whiter than white or blue-white. And this is, in actual fact, a bottle of tonic, and it's got a chemical in it that will do the same sort of thing. And you probably think it very odd if somebody in actual fact was drinking this under UV light, and it would look a sort of little bit Jekyll and Hyde-ish, because their tonic would be all blue as they were drinking it. But that's a process of the light coming back, because the chemicals already have that ability. It's not the same as what the glowworm does. Mike's going to show you something similar to what the glowworm can do.
Right, now you've seen several examples today of reactions producing energy. It's not at all unusual for chemical reactions to produce light energy. Flames do it, explosions do it. But it's very unusual for chemical reactions to produce light energy and nothing else, no heat or sound. We've got 2 chemicals here, one called luminol, for obvious reasons, that react together to produce light and no heat or sound. Can we have the lights down, please? And you can see the mixture that I've made is glowing where the 2 chemicals meet, and will continue to glow for some time, but as you can see, it fades fairly rapidly. Anne's going to show you 1 or 2 reactions that can be sustained for longer periods of time than this.
That is the process called chemiluminescence. And as I said, when you find something as interesting as that, you try and understand it so you can make it better. And we have got a reaction here where we are going to make the reaction produce light, but this time the light's going to last, and we can also choose the colour of the light. We need to add hydrogen peroxide to get the reaction going. And you can probably already see that we've set our colours into the reaction. The blue one's still a bit shaky. Okay. And there we have a light that will last for probably 12 hours, and we've got a different colour light. And when you understand chemistry and you can make it do that thing, that's great fun. And that's what we're going to get you to do. Can we have the lights up for a minute, please? Because you've all got in front of you, or near you, some tubes with exactly that reaction in as it's been produced for fun. So what I want you to do is to break the tube to the little capsule to allow the chemicals to mix, and then you will either have a necklace that you can put on or a tube that would in actual fact light up the region around you. And that reaction is just for fun, especially if it's done as necklaces or bracelets or something like that. But the light will last for some time. The reaction is really originally sold for something much more serious. It's sold as a safety light because you'll notice your tubes are completely cold. You wouldn't be able to hold an electric light bulb that was glowing like that. It would be too hot. And if you had the danger of an explosion, like the ones Mike was talking about earlier, you had to go into a gas-filled room, then this would be safe. There's no spark, there's no heat, it couldn't cause an explosion. And the fire brigade and the army and people under the water and miners could use these, in actual fact, to have a safe source of light that's guaranteed for 12 hours. That when they needed it, they could break it and it would give them the light for whatever the packet on the safety light said that it would last. What we've tried to show you is that chemistry is fun and that it's exciting. And we've only had time to take a few of the Earth's resources, the Earth, the rocks and minerals, the sea, the gases in the air and the oil, and show you just some of the things that you can in actual fact make from them that you use every day. And we hope you've seen that if you really understand what the molecules are doing, that's what makes it fascinating and interesting. And that means that you might one day be able to do some of these things. You might be able to discover how to protect the rainforests, or perhaps you'd like to learn how to feed the people who are suffering from famine. Or perhaps you'd like to be able to actually make the molecule that the scientists in America want to go into their microcomputers, or invent a superconductor. Or perhaps you'd like to cure a sick animal, or help somebody who's suffering from cancer, or AIDS, or diabetes. If you want to be able to do any of these things, then you need to understand the molecules that make you, and the plants, and the animals, and the rocks, and the minerals work, and why they do the things they do. And that's what chemistry is about. And if you want to do these things, you need to understand chemistry, because chemistry is your world.